Welcome back to the Computer Lessons.
Wearable technology is the ultimate frontier of electrical engineering, where the human body becomes the primary data source for digital systems. Engineers must compress complex laboratory equipment into a form factor that fits comfortably and discreetly on a human wrist today. This requires an unprecedented level of integration between human biology and advanced hardware components. The core of every fitness tracker is the PPG sensor, which stands for photoplethysmography to measure blood flow. It uses green light emitting diodes to illuminate the skin and photodiodes to measure the light reflected back. Because blood absorbs green light, the fluctuations in light intensity correspond directly to the pulses of your heart. Engineering accurate PPG sensors requires overcoming the noise caused by ambient light and physical movement during intense exercise. The sensor must remain flush against the skin to prevent light leakage, which would ruin the data integrity. Advanced algorithms are then applied to filter out the motion artifacts and extract a clean heart rate signal. Beyond heart rate, these devices utilize micro-electromechanical systems, or MEMS, to track physical motion and orientation. Tiny accelerometers and gyroscopes measure the gravitational forces and angular velocity acting on the device. These microscopic machines consist of moving silicon parts that are smaller than a human hair, but incredibly precise for tracking. To count steps or detect specific exercises, the device processes raw MEMS data through complex machine learning models. These models identify the specific rhythmic patterns of walking, running, or swimming, while ignoring random arm movements. This digital signal processing happens locally on the wearable to minimize latency and preserve user battery life. Blood oxygen monitoring, known as SpO2, uses red and infrared light instead of green light to measure hemoglobin saturation. Oxygenated blood absorbs more infrared light, while deoxygenated blood absorbs more red light. By calculating the ratio between these two wavelengths, the device can estimate the percentage of oxygen in your bloodstream. Advanced smartwatches now include electrocardiogram functionality to detect irregular heart rhythms like atrial fibrillation. This works by creating a closed circuit through the user's body when they touch a secondary electrode. The device measures the tiny electrical impulses generated by the heart with medical-grade precision in a consumer-ready package. Miniaturization is achieved through system-in-package technology where multiple chips are stacked vertically into a single tiny module. This SiP architecture includes the processor memory and wireless radios, while taking up 60% less space than traditional motherboards. It is the only way to fit smartphone-level power into a device that weighs grams. Thermal management in wearables is uniquely challenging because there is no room for fans or large heat sinks. The chassis itself must act as a radiator to dissipate heat away from the skin. Engineers must strictly limit the power consumption of the processor to prevent the device from becoming uncomfortably warm during use. Battery technology remains the primary bottleneck for wearable engineering due to the physical limits of lithium-ion chemistry. High energy density is required to provide multi-day battery life in a tiny volume. Curved battery designs are sometimes used to maximize every available cubic millimeter inside the circular or rectangular watch casing. Wireless charging for wearables often relies on small magnetic induction coils to ensure perfect alignment without ports. This maintains water resistance by eliminating physical openings that could leak. However, the small coil size limits the charging speed compared to smartphones, making efficiency critical for a fast top-up before a workout begins. Display technology has shifted toward LTPO-OLED panels, which allow for always-on functionality with minimal power draw. These displays can drop their refresh rate to as low as 1 Hz when the screen is idle. This allows the device to show the time constantly without draining the limited battery reserves. Material science is vital for biocompatibility, as the device is in constant contact with the skin for days. Aerospace-grade titanium and specialized ceramics are used for their strength and hypoallergenic properties. These materials must also be transparent to radio frequencies to allow Bluetooth and Wi-Fi signals to pass through easily. Water resistance is measured in atmospheres and requires precision-engineered gaskets around the sensors and buttons. Devices rated for swimming must withstand the dynamic pressure of moving through water. Acoustic membranes are used over the speakers to allow sound out while keeping high-pressure water molecules from entering the internal circuitry. The integration of GPS antennas in a small metal frame requires complex electromagnetic simulations. The human body itself can block satellite signals, so the antenna must be positioned optimally. Multi-band GPS systems are becoming standard to provide meter-level accuracy, even in dense urban environments with tall buildings blocking signals. Sleep tracking leverages the combination of heart rate variability and motion data to estimate sleep stages. By detecting the lack of movement and the slowing of the heart, the device identifies deep and light sleep. This data is correlated with respiratory rates to provide a comprehensive view of the user's recovery. Electrodermal activity sensors measure the skin's conductivity to track stress levels in real time. When you are stressed, tiny amounts of sweat change the electrical resistance of your skin. This biometric data allows the device to suggest breathing exercises or rest when it detects high levels of physiological strain. Skin temperature sensors use high-precision thermistors to detect changes as small as 0.1 degrees. This data is used for cycle tracking and early illness detection by monitoring baseline trends over time. Because ambient temperature affects the reading, the device often uses a secondary sensor to subtract external environmental noise. Connectivity in wearables relies on Bluetooth Low Energy to maintain a constant link with a smartphone. BLE is designed for periodic bursts of small data packets, which is ideal for notifications and health syncing. This protocol is essential for extending battery life while keeping the user connected to their digital life. Local artificial intelligence is increasingly used to process health data directly on the device for privacy. Neural engines within the SiP can identify fall detection or car crashes without sending raw sensor data to the cloud. This edge computing approach ensures that the most sensitive personal data remains on the user's wrist. Haptic feedback is provided by linear resonant actuators that simulate physical clicks and notifications through vibration. These actuators must be powerful enough to be felt through clothing, but small enough to fit. Precise control over the vibration frequency allows the device to communicate different types of alerts silently. The user interface of a wearable must be highly optimized for a small circular or square touch surface. Large touch targets and digital crowns are used to navigate menus without obscuring the screen. This requires a custom operating system that prioritizes glanceable information and voice-driven interactions for the mobile user. Medical regulations like FDA clearance are required for any wearable that claims to diagnose heart conditions. This adds years of clinical testing to the development cycle of a new sensor. Engineers must ensure that the hardware can maintain its calibration and accuracy over years of constant real-world use. Future wearables are moving toward non-invasive glucose monitoring using infrared spectroscopy. This would allow millions of people to monitor blood sugar without painful finger pricks. It is a monumental engineering challenge that requires filtering out the interference from other molecules in the interstitial fluid right now. Smart rings represent the current peak of miniaturization by removing the display entirely. They pack the same PPG and MEM sensors into a form factor that looks like standard jewelry. The engineering focus here is entirely on battery life and data synchronization without a traditional user interface present. The software ecosystem surrounding wearables uses the collected data to build a digital twin of your health. Cloud-based servers analyze long-term trends to provide insights that a single measurement cannot. This creates a feedback loop that encourages users to improve their physical well-being through constant and personalized data. As we bridge the gap between our bodies and our machines, we must also consider the invisible risks. In our next episode, we dive into the world of cybersecurity and networking, where we explore how data is protected. We will examine the constant battle between encryption systems and modern digital threats.
The integration of health sensors into our daily lives has changed the way we understand our own bodies. This wearable revolution is only beginning as sensors become smaller and more capable every year. Do you trust the data from your wearable for medical decisions, or do you only use it for fitness? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching, and keep learning.